go. Problem number 81 from page 337. We're supposed to find all complex zeros, and by zeros we mean roots, and give exact answers, list multiple zeros as necessary. And we happen to have a quartic polynomial this time, so it might take us a while to find the roots because there are 4 of them. We're going to have to do a little bit of searching. What I'd like to start with is finding my APRR list, so I know what rational roots are potential roots. And so remember, to do the APRR list, you look at the constant, and that gives you your potential numerators, plus or minus factors of 4, so plus or minus 1, 2, and 4. And then you also look at the leading coefficient, which is 1 this time, and all the factors of that will be your potential denominators, so just plus or minus 1. And so if you put together all of those numerators over all of your potential denominators, in this case we get a really short list, plus or minus 1, 2, and 4. So if this polynomial has any rational roots, they have to be numbers from this list of 6 numbers. Either 1, -1, 2, -2, or 4, -4. Okay, the next thing we're going to do is the synthetic division chart, and this is a way to organize all of our synthetic divisions into one place and make it go faster. So put all the coefficients of your polynomial in the 0 row, and -4 is going to be in the remainder column. Give yourself plenty of room above and below. You don't necessarily know how far you're going to end up going. And then let's start by making the 1 row. So put the 1 in the box, bring up the first number, multiply it by the number in the box, and add the next number in the 0 row. 2 times the number in the box, add the next number in the 0 row. -7 times the number in the box, add the next number in the 0 row. 4 times the number in the box, add the next number in the 0 row. Okay, that is really encouraging. We got 0 right away, so we have a root at x equals 1. 1 root down and 3 roots to go. So we're still going to need to keep searching by just making rows in the synthetic division chart. And I'm going to pause and go ahead and fill in a bunch of rows. And then we'll look and see how it's going. And you could do the same thing. Okay, let's look and see what we have. It took me a while. I had to do a lot of rows, but I did find another root at -4. Now you might be wondering, why did I waste my time doing a 3 row or doing a -3 row when there was no way those were going to be roots, because 3 and -3 are not in my APRR list? Well, you're right. It wasn't necessary, but I'm just in the habit of always going in order and not skipping rows because of what's coming next in this unit. You're going to want to go in order and not skip because you'll be looking for clues in the remainder column, and sometimes you won't see those clues if you skip numbers or you don't go in order. So that's just a habit that I'm in. Okay. Now we have a root at 1 and we have a root at -4. So we have 2 of our roots and we have 2 more to go. So at this point what we want to do is what I call whittling down the problem to a quadratic. So I'm going to take either my root 1 and divide it into the -4 row, or I'm going to take my root -4 and divide it into my 1 row. Either way, it doesn't matter. It's going to take it from right now being cubic and whittle it down to being quadratic. So I'll just go with the first one that I said, which was I'm going to take my root 1 and divide it into the -4 row. So I'll do that over here off to the side. 1, and then the row was 1, -3, 3, -1. That is a cubic polynomial. Do regular synthetic division, bring down the 1, multiply by the number in the box, write it here and add, multiply by the number in the box, write it here and add, multiply by the number in the box, write it here and add. There's our remainder of 0. This is the quadratic we were looking for, x squared minus 2x plus 1. Set that equal to 0 and solve for the final 2 roots. If it's factorable, great, factor it. If not, use the quadratic formula. This one is factorable. X minus 1 times x minus 1. So we happen to get x equals 1 again and x equals 1 again. So our 4 roots are x equals 1, 1, 1, That's called a triple root, or we can say it has, here's how the book would say it. It has multiplicity. So fancy. Multiplicity 3, because there are 3 of them. 1, 1, 1, and the fourth root, -4. That's the answer to problem number 81.